All right, well, good morning, everybody, and welcome to the latest in the NOLCA webinar series. My name is Ron Peterson. I'm the Executive Director of NOLCA. So today's webinar is GPR Utility Data Tips and Tricks, and it's being provided by Sensors and Software. Sensors and Software was the first NOLCA accredited GPR manufacturer and training program in North America. So we've been really thrilled that they took that step and climbed on board to support NOLCA and also the competency standard for GPR. So with us today is Greg Johnston. Greg's back by popular demand. He does a wonderful job with this. And with that, Greg, I'm going to turn it over to you.
All right, great. Thanks, Ron. So again, my name is Greg Johnston. Just to give you a little introduction, I'm with Sensors and Software, and actually this month I'm coming up on 29 years with Sensors and Software. So I have a fair bit of history with ground penetrating radar. All right, so let's get going. All right, so today's topic is called tips and tricks. And so what that means is that it's really geared for people who are already familiar with GPR to locate utilities. So I do assume a bit of knowledge, and I won't be going into a lot of theory as we go along, but you will see some. All right, and first slide though, just to get everybody on the same page. So GPR is a technology that uses radio waves to image into the subsurface. And this animation really shows what can be done. So we're taking radio waves, we're inside any GPR system, there's a transmitter. So it's transmitting the energy into the subsurface. And where there are changes in the subsurface, that energy reflects and can come back up to the surface and be picked up by the receiving antenna. That's also part of the GPR system. And that's the way you detect things. Now, I'll point out that we are dealing with radio waves. So this animation is about 1 billion times too slow compared to how it actually happens. So the energy is traveling near the speed of light as it goes into the subsurface. And so you really see it. This is really slowed down, but it does show the concept. All right, let's get everybody on the same page by briefly going through what I call line scan. So line scan data collection is what you're going to see when you turn on a GPR instrument. Usually there'll be some sort of way of collecting data. So we call it line scan. So there'll be a line scan button that you press. And here's a little video that shows somebody pushing the system along the ground and then what's visible on the screen as they push it along the ground. So a lot of these systems are triggered by an odometer. So as the odometer moves a few centimeters or inches, it fires the transmitter, and the transmitter sends energy into the ground. It collects the signal coming back, and you see an image on the screen. And so one of the really nice things about GPR is the fact that you get a real-time image. You get this cross-sectional view of the data as you're collecting it. So you can respond in real time. So in this case, we've collected some data down. Here's an image. And as I mentioned in my last webinar, as complicated as GPR images can look, there's really two basic types of responses to look for in the data. And the first, a lot of people are going to be familiar with hyperbolas. And so there's a number of hyperbolas visible in this data. We've got these inverted U shapes, hyperbolic responses, and there's a few of them. There's even more scattered through in here. I've got some arrows on them. And those are from objects buried in the ground. Those are either utilities, but they could also be rocks. They could be tree roots. They could even be localized areas of soil with a high water content. Anything that causes greater contrast reflects energy. The other thing to look for are boundaries. So we see a number of boundaries in the data here, this flat lying undulating line going along here. And a boundary is really just a change from one material above to a different material below. And so this could be a change in soil type, but it could also be a change in the water content of the soil, which is often the case in sandy soils. And in this example, this is actually a terrific area for GPR. we are seeing almost 6 meters down, so we're getting 20 feet. And this is with just a standard utility type locator, so a relatively high frequency. Okay, so what's the tough thing about GPR? The ground is a complicated place. There's a lot going on in the ground. And therefore, because GPR is sensitive to every change in the subsurface, you can get a lot of information in your image. There's a lot to look at. And I get people who ask, well, how do I set it to just look for pipes? And say, well, there's no settings like that. If we had a setting like that, I would just put in the setting for gold bars and go to town. But there's no way that we can do that sort of thing. GPR will create a cross-sectional image of the ground, and you're going to see all the changes in the subsurface. And so not just the target you're looking for. So, the big part of GPR is interpreting the data, being able to look for the object you're looking for and ignore the things that you're not interested in. And you got to realize that some objects produce weak signals. It's all due to contrast. The soil absorbs the signal. Some soil absorbs it faster than others. So people will know that clay soils are generally not the greatest for GPR. We can usually only see 2, 3, 4 feet in clay. But when you're in other types of soils, you can get up to 10, 20 feet even in some cases. And the other thing is the data has to be interpreted. We do not have software yet. We don't have AI software that goes in and says your target is here. It's coming. That sort of thing is getting better, but we're not there yet. And so a lot of the images you have to interpret. You have to look at it and understand what's going on. And I'll make the big point of, a lot of data interpretation is based on context. You're going to interpret data differently on the street of a major city than you are in a farmer's field, than you are on a mountaintop. And therefore, context is very, very important when you're looking at these images. And just knowing where were you, what was the situation. And so I often ask people for, when they show me data is, show me where it is. Show me some photographs of the site to help me understand what you're looking at. And so these are the challenges of using GPR. And I'm sure that many of you have experienced these challenges and not known what to do. So today I want to talk about a few tips and tricks that can sometimes help with some of these limitations of GPR. And I say sometimes because I'm not going to solve all your GPR problems today, but hopefully give you a few more strategies to solve a few of them. And most importantly, understand your GPR data better. So let's start off with, as simple as it can get, just crossing utilities with ground penetrating radar. And anyone who has used GPR for utility locating was taught or quickly discovered that the best way to detect utilities is by crossing them at 90 degrees. When you cross a utility 90 degrees or perpendicularly, you will see a hyperbolic response on the screen. And if you collect a number of parallel lines and mark the top of the hyperbolas, you can follow the path of that utility. And so in this case, you can see that the operator is putting flags in the ground to mark the path of the utility as he crosses it over and over again. And each time you collect a line that crosses the utility, you hope to see something like this. Hyperbolas with a consistent depth and similar character. This is what gives you the confidence that you are following the same target and having success. So here's another example that shows, in this case, we have multiple utilities. So the lines are longer, so we have multiple utilities that are visible. And this example I like because it really shows what I'm talking about in terms of character. Each line you can see, on each line you can see that each of the hyperbolas is slightly different in terms of shape, width, and strength. And this is what makes it easy to identify each utility on each line. So for example, we see this shallow one here, and we can mark it 1 on all 3 lines. We can see similar character, similar depth. Hyperbola number 2 is very distinct. It's very broad, and so we see that easily in the 3 lines. Number 3 is a bit trickier, but if you know what to look for, you can see the hyperbolic shape. You can see it's generally the same. The one on the second line isn't that good, but based on being convinced that you see it on line 1 and line 3, you can easily say, yeah, okay, I think I can see that hyperbola on line 2. I'm convinced. And then the last one, hyperbola number 4, you can see same character, same sort of depth. So that's the type of things you're looking for to follow your utilities. Now let's talk about crossing at an angle, crossing at different angles over a utility, because you don't always know what way a utility is running. So you can't always collect GPR data lines that cross them perpendicularly the first time. So how do GPR responses change when you cross utilities at different angles? So we know if we cross it at 90 degrees, we're going to see a hyperbolic shape. But if we cross it at 45 degrees, what happens to that hyperbola? Well, that hyperbola gets broader. So you'll see a hyperbolic shape, but what you're going to see is that it looks a bit broader compared to crossing it at 90 degrees. And if you run a line right along the top of a utility, this is a tricky one in terms of people kind of understand what's happening, but you end up with a flat line. And the way that happens is, just remember, the GPR is always the same distance away from the pipe or the utility when you walk right along the top of it. It's always at the same depth. Now, if that utility was sloping, you would see the slope. It wouldn't be a flat line. It would end up being a sloping line, because the distance between the GPR on the surface and the utility at depth would be changing as it sloped. But basically, you would end up seeing a line that was, tilted or not. And so that's a tricky one. Every now and then, somebody will happen to walk right along the top of your utility and may not even know it. And it's when you turn 90 degrees to that and collect some data that you realize, oh, that flat line ends up being is actually a utility. It's not a boundary or something like that. And so we get examples like this, where if you look at hyperbola 1 and hyperbola 2, you can definitely see that hyperbola 1 is broader than hyperbola 2. And so what does that mean? So one interpretation is that hyperbola 1 is from a utility that has a very large diameter. And that's not an unreasonable interpretation. However, there's another interpretation, which is usually the right one, which is that the GPR line crossed the utility at an oblique angle. So you actually had a situation like this, where as you went across utility number 1, you went at an angle, it made it look broader. And then when you went across utility number 2 at a closer to a right angle, it was a tighter hyperbola. So it's usually a situation like this. Now, it only takes a minute and a couple more lines to determine which interpretation is correct. If you cross utility 1 at a different angle and the hyperbola gets narrower, you know that it's not a large diameter utility. But what I want to point out from all this is, expect to see these broad hyperbolic responses and at times misshapen hyperbolas as well. We've got images here that show, real data, the type of things that you see, and broader hyperbolas are common, but also kind of misshapen ones. And it all depends on the angle that you cross things, the soil conditions. There's a lot going on, but at least recognize them and say, you know what, I think there's an object here. I'm just not crossing it at the right angle. Let me do a little bit more homework and try to narrow down where it's coming from. Having said that, so once you find a utility, how do you mark it? How do you indicate that on the ground? And I want to show this video, and so you can follow what's going along. And this is what happens with GPR. You really don't find an object until you've crossed it. So you go across it and you say, oh, well, wow, there's a big hyperbolic shape. I'm going to back up. And you follow the red line back and you realize, okay, now I'm right on top of the hyperbola. So that's where the object is. Now I'm going to mark it, and watch what he does here. He puts a flag on either side of the GPR system, moves it out of the way, and then actually puts the positional flag in the center between those two flags. Now, I want to show the why. So here's the situation. You've got a GPR system, you've got a pipe buried in the ground that you can't see, and you move across it and you see a hyperbola. So you back up onto it and you put a flag in the ground. Good to go. And you move away, and that's your mark on that's your marking of the utility. Well, that's actually wrong. You lucked out. You lucked out here because you happen to have crossed the utility at 90 degrees. So let's look at another situation. So now your first line, you haven't sort of figured out the orientation, and you collect data across. You see the hyperbola. In this case, you can see it's a broader hyperbola. So you do have a sense that you've crossed it obliquely. And when you back up, you can still pinpoint exactly where it is. You can still go to the top of that very broad hyperbola and mark it. And obviously here, when we move out of the way, you have not marked that utility in the right spot. So it's very obvious in this case. So let's look at the right way of doing this, which was shown in the video. Cross the hyperbola, back up to it, put a flag on one side, a flag on the other side, move the GPR system out of the way, and put a flag in the center. That is how you locate. And that is going to put you on it every time. And so again, this works even if you're crossing obliquely. So again, you cross it, see a oblique hyperbolic response or a broader one, you back up onto it, you get to the highest point, which admittedly is not always that easy to get exactly where the highest point is. You put a flag on one side, flag on the other side, move the GPR out of the way, go to the midpoint and put it on, and you're going to be on that target. Okay, so I watch a lot of people do it the other way. And a lot of times when you cross at 90 degrees, you're going to be right, but you're right just through dumb luck rather than proper technique. Okay, let's talk about other responses that you see in the data, which can throw you, which can cause problems with understanding data. And this happens not just for utility locating, this happens for any time you're using ground penetrating radar to look into the subsurface. And the first thing I want to talk about is what we call ringy responses. And ringy responses are when this happens. This is an example of a ringy response. So there are times when GPR energy can get trapped in a shallow layer and reflect very strongly up and down. And so the energy, rather than the majority of it going down deeper, it actually reflects from that boundary and goes back up, hits the surface, reflects back down, and does the same thing over and over again. And it's not as common as you think. You would think that this would happen all the time. It does take a special situation where there's a very high reflection coefficient on the bottom of that boundary. And one that I can show you, which as utility locators, you're never going to deal with this, but ice over water. Ice over water causes this thing, this ringing or multiples, because the energy just bounces multiple times in the ice. And the reason is that there's a huge contrast between ice and water, and that gives us a very strong reflection coefficient, and therefore a lot of energy reflects. And that energy ends up bouncing up and down. And so if you're an ice profiler, which GPR is used for measuring ice on ice roads. If you ever watch ice road truckers, and you'll see stuff like this, they're taught that only look at the first response. The first response is actually the bottom of the ice. All these other responses are just multiples of the energy bouncing up and down. Now, I'm saying you don't see that, but you do see that sometimes in situations that you'll run into. And the classic one is puddles of water. And if your GPR system goes into a puddle of water that's just deep enough to immerse the entire bottom of the GPR, and specifically both the antennas, in the water, I know they're in the system, but basically if there's no air gap, if it's just goes from GPR system to water to pavement underneath, you're going to get energy can get trapped in that layer, and because it's a huge reflection coefficient from water to pavement, you can get the same sort of thing. And this is what you'll see in the data. And if somebody's interpreting this data perhaps later and didn't realize that you walk through a puddle, they might say, whoa, something funky's going on there. Like, I can't say 100% it's a utility, but maybe this is disturbed soil or something that maybe they buried a utility down here, and what I'm seeing is the trench that was dug. Well, that's all the wrong interpretation. And so it's important for the operators to identify that, yeah, I went through a puddle at this point, so you might want to be careful of your interpretation of the data here. And so what happens is the energy gets trapped, and because the puddle is an odd shape and it goes out to sort of zero depth, you can get these hyperbolic looking tails on the sides of things. The other thing that you're going to see is, because water is such a slow material for GPR waves to go through, you're gonna see this dip at the top of the signal. And up in here, you can actually see the signal dipping down, and that's because of going through the water. And so you should be able to identify it through that. But the easier thing to do is just mark it and say, you know, this was through a puddle. So be careful of puddles. And what I don't want you to take away from this is that Greg said, I can't collect data because it rained. No, if the ground is dry, if the ground is wet, that's fine. As long as there's an air gap between the wet ground and the GPR, and I don't mean a significant air gap, I mean that fraction of an inch, is absolutely fine. The data, you can see on both sides of this puddle, the data is absolutely fine. It's only when you're immersed in the puddle that this effect will occur. The other type of Ringy response that you get is from metal debris. And I'm sure a lot of people have seen this. A lot of people know this theory, but I think it's useful for me talking about it again. When you have shallow metal, if you have metal that's either on the surface, maybe visible, shallow metal just under the surface, and in my experience, the metal has to be within about 18 inches of the surface. Deeper than that, this effect doesn't seem to occur as readily, or it's not as easy to see. But what happens is the GPR signal goes down, it hits that piece of metal. Well, that piece of metal, if you think about it, an antenna is a piece of metal. An antenna is a movement. And so when the transmitter sends energy down onto this piece of metal, energy can get trapped on that piece of metal and it will ring. It will do this. And it will bounce back and forth, except it will bounce back and forth many, many times. And so you get this occurring. The signal will ring. So you get energy that's re-radiated from that piece of metal over and over again. And it's not, you know, that metal is not going to be as good of an antenna as the one in our GPR system. So it does a really bad job. It just radiates the energy over and over again. And so what you end up seeing is something like this in your data. So, you know, people have seen this when they go over metal on the surface. And what's happening is the energy is getting trapped on that metal. It's bouncing around on the metal. It is not penetrating the ground. So when you see this sort of response, it looks like, wow, look at how deep I'm seeing. You're not really seeing deep. All that energy is trapped on that piece of metal and just radiating at different times. So it's not actually traveling to depth. So be very cautious of this. And also keep in mind that it's usually a piece of debris. It's a small enough piece of metal that you can energize it. If the metal gets very large in size, it gets really hard to energize the whole thing. And if you had a pipe that was a metal pipe that was 500 feet long, technically it would ring, but it would take so long to travel to one end and reflect from the other and come back that you would not see it like this. The reason you see this ring is because this metal is short enough that the energy can just go from one end to the other and turn into an antenna. So some of you more than likely have encountered things like this and wondered, what do I make of this? Here's another example of a piece of metal. And oftentimes it rings. Eventually, the energy will slow down and get absorbed. And so you will sometimes see an end of it. But the examples before, it looks like it goes forever. But if you go down deep enough, eventually it will fade out. Okay, so those are a couple things to watch for in terms of ringiness in the data. Now, I want to talk very briefly about velocity calibration. And if you've had any training with ground penetrating radar, you have more than likely done some sort of velocity calibration. So here's an example of a GPR cross section. And you can see we've got, in the shallow part at the top, we've got a number of hyperbolic responses in here. And then down deep, we've got this really big hyperbolic response. And so here's what you do your due diligence. You say, okay, let's do a velocity calibration. And I do a velocity calibration on one of the hyperbolas that are shallower ones, and I get a velocity of 0.1 meters per nanosecond or 0.33 feet per nanosecond. And I look on my table of typical velocities for different materials, and that comes in at moist sand. 0.1 or 0.33 feet per nanosecond is generally a moist sand. Okay, so nothing surprising there. So then I do a calibration on the deeper hyperbola, and I get a velocity of 0.3 meters per nanosecond or 0.98 feet per nanosecond. And I look at my table and I go, air. What's going on? This looks like it's a giant. I look at the image and my first thought is some sort of cavern or a buried tank, something with very large diameter is buried in the ground. And in fact, I have a story about this, which I'll tell in a second. But let's just think about what the velocity calibration has just told us is that the velocity of the material between the GPR system and that object is traveling at 0.3 meters per nanosecond, which some people are going to know is the speed of light. So the speed of light is 0.3 or about a foot per nanosecond. And what that means is that this object is not in the ground. This object is in the air, because that's the only way that that signal can travel at the speed of light is it's got to be in the air. And so I had a guy one time who called up and he was pretty upset, and he had rented one of our GPR systems. And the story, I'm pretty sure he was a treasure hunter, just from things I picked up during the conversation. But he collected some data like this. He saw a big hyperbolic response down deep, and he thought, this is it. I found my treasure. And so he ended up, he told me he paid $10,000 for a guy to bring in a backhoe into this very remote area. And he dug a hole 7 meters deep. He dug a hole like 20, 22, 23 feet deep. And he said there was nothing there. And he was super upset at us. And he thought our GPR system was, a bunch of bad words. But as it turned out, he dug for an airwave. He dug for a signal that was not in the ground, signal that had traveled through the air object. And anybody who's done any sort of work with GPR needs to know that not all the signals that you see are necessarily in the ground. So let's talk about airwaves. Airwaves are the idea that some energy, not a lot of energy, but some energy will leak out from the GPR, from underneath the GPR system, and it can bounce off of things. It can bounce off of buildings. It can bounce off of trees and metal posts and power lines over your head and all those things. Not a lot of energy, but a little bit. And what you will see in your data is hyperbolic shapes or flat shapes. But there's always clues. There's always a good clue that these are not in the subsurface. If you look at this example, you might look at it and go, oh, okay, they found a fairly large object around 2 3/4 meters in depth. But part of you says, you know what, I better do my due diligence. I better do a velocity calibration and make sure. And when you do a velocity calibration, it comes out to the speed of light. And you go, okay, so that's not real. In this particular case, this was the target. Now, usually at this time, people who are using, if they've never heard of airwaves from GPR, they're freaking out because they're thinking, how many things have I missed over the years that are probably airwaves? And the thing I want to point out is that airwaves occur after the GPR, the real GPR signal has faded out. Once all the GPR signal has been absorbed by the ground, that's usually when you start to see the airwaves. Because these signals are very weak. They're often just above the level of the background noise in the bottom of the GPR section. So they're a bit stronger than that. And so if you apply a gain and you amplify the signal, then these things start to pop out in the bottom of your GPR section. And if you don't know what to do with them, then you could make a misinterpretation and perhaps cost somebody money or time or that sort of thing. So be very cautious about airwaves. They are there. And even though, somebody will say, well, my GPR system is shielded. They told me it was shielded. Well, even when they're shielded, energy can still leak out into the air. And let me give you let's go back to this data and let me show you a little trick here, which just allows you to identify where the object is. So remember, the speed of light is about 1 foot in 1 nanosecond. So if you happen to have a time scale on your GPR, which not everyone does, they don't often have a time scale, they usually have a depth scale. But if you happen to have a time scale on your data, you can look at that time scale and you can figure out how far away that air object is. So in this case, I look at it and I say, okay, it's around 54 nanoseconds. So it took 54 nanoseconds for that air wave to come back. So how far away is that air object? Well, if I walk to this point on my GPR line and I looked a certain distance away, there's going to be an object, no doubt, in the air. And the thing you have to remember is that you have to divide the time value by 2. So in this case, it comes out to 27 feet. So 54 divided by 2 is 27 feet. And the reason you divide by 2 is because the energy has to leave your GPR, go out, reflect from that object in air, and then come back. So it's actually going the distance twice. So you have to divide by 2 to get the right answer. So if I stood at this point on my GPR line and I look 27 feet away, there's going to be something in some direction. Could be above my head, could be off to the side, but it's going to be there. And then also be careful of walking up to buildings because energy can go out ahead of the GPR and bounce off the building, and you end up seeing things like this in your data. So it looks like, oh, I'm just coming up to an interesting hyperbolic response, and oh, I hit the side of the building. So maybe it's under the building. Very unlikely. And if you do a velocity calibration and fit half the curve, you will often see, you can measure that it's the speed of light and confirm that this was an air object. This was actually the side of the building or something on the side of the building. So maybe a balcony or something like that. Usually these things that protrude from buildings and metal objects become very strong targets and energy will bounce off of them. So watch for that in your data. Now, the trickiest air object is something that's parallel to you. So if you're walking parallel to a metal building and you get a flat response in your data, that could be the side of the building. It's possible. Do the same time trick there and say, okay, I see a response in my data, flat response at about 30 nanoseconds. And if I'm walking 15 feet parallel to a metal object, then there's a real possibility that that reflection is an air reflection from that object and not a boundary. And I've watched people get data like this and say, oh yeah, we obviously see the water table right here, right? Flat reflector, looks good, water table, everything matches, great interpretation to put in my report to the client. And totally wrong, because it was an airwave and they didn't do their due diligence. One to really watch is, especially when data is taken out of context, if you had this data and you didn't see where it was collected, this is a very interesting target. What is this flat thing like in here? Some sort of large object buried in the ground or major boundary or something. But then as soon as you realize, oh, this was collected under an underpass, energy went up and bounced off the top. And in fact, energy went up and bounced twice off the top. It went from the GPR system, it bounced off the ceiling, came back down, bounced off the road, came back up, bounced off the ceiling a second time, and came back down to the GPR system. So we got the first reflector and the second reflector. Both of them are airwaves. Both of them should be totally ignored. And again, you take your data out of context and you're going to make mistakes. Okay, let's talk about something a little bit different, grid scan. And so hopefully I'm preaching to the converted here, but if you're not collecting grid scans, I'm going to try to convince you of the benefits of collecting grid scans. And if we jump back to our data logger here, grid scan is often one of the other options when you're collecting data. It's a second type of data collection, and that's available on the GPR system. So when we go into grid scan, the idea is that I have an area that I am particularly interested in because I'm looking for something in particular, or if I'm a utility locator, it's a very congested area. I've walked around on the surface and I've marked all hyperbolas all over the place, and I can't figure out which ones are lining up with which. I've got marks all over the surface. I can't make head or tails of it. So that's when you should be thinking, you know what, I'm going to collect a grid and I'm going to sort this data out. And so we're going to cover an area in a very regular pattern of X lines and Y lines. So Y lines in both directions to cover the whole area. Let's talk about this for a minute. So let's look at setting up a grid on the data logger. And so here's a little video. You go into grid settings and you can change the size of the grid. I know it's hard to see the numbers, but this is 5 meter by 5 meter grid, 10 by 10, 15 by 15, 20 by 20, 25, 50. And some of our systems will allow you to do grids up to 100 meters. And then coming back down to using the minus button to come back down to a smaller size, 5 meters. And then the next thing you're going to do is decide how many lines are you going to collect? What's the line spacing between each of the grid lines in the data? So you can go very coarse, you can go very fine. It's a user variable. And then you can also decide, which pattern am I going to do? Am I going to walk all the lines in the same direction? Or am I going to go to the far side of the grid, turn around and come back and collect data on my way back, which is called forward reverse. So you either do forward reverse or you go all in the same direction. And then you can get into, you don't have to just collect a square. If it's rectangular, you can modify the size to collect a rectangular grid. And the whole time that you're doing this, one piece of information is on the screen, and that is the diagonal distance or the hypotenuse, because that's going to help you to set up that grid out in the field, knowing how far apart those corners should be. So here's our grid where we're setting up 5 meters by 5 meters, and the distance of the hypotenuse or the diagonal is 7.07 meters. And it just helps you to set up the grid. The other thing we need to talk about is the line spacing. So what's the distance between grid lines on the ground? And if you think about it, this distance is what decides how detailed your grid collection is going to be and how much work you're going to have to do to finish it and how long you're going to spend in the field. So obviously, the coarser the line settings, the quicker you can get that grid done and get out of there. But I'm going to argue that your grid, your line spacing has to be related to the object you're looking for. That has to be a factor when you're trying to set up your grid. So let's look at subsurface objects. What are things that we could be looking for? As utility locators, we're probably looking for long, linear, cylindrical objects, right? But we might be looking for other things. We might be on a task one day to look for storage tanks. So larger diameter, but smaller in physical length. Or we might be looking for something spherical. If we end up doing a forensics job or an archaeology job, then we could be looking for objects that are spherical or cubic or all the variations in between. They could be rocks, debris, point objects of interest. And then you look at boundaries. In some cases, you might be looking for boundaries. You might want to find the bottom of the base course underneath a road or something like that. That's a boundary. So all these things come into play in deciding how far apart am I going to collect my lines. Obviously, the larger the physical size of the object, the coarser I can set my line spacing. But if you want to collect data the best, if you want the best data for your grid, relates to the antenna frequency you're using. And so you should collect a grid like you're mowing your lawn with the GPR antenna. So it relates to the length of the GPR antenna. So for example, if we look at these different frequencies, we have a 100 megahertz system that has a 1 meter long antenna. Well, that means our ideal line spacing is 1 meter for 100 megahertz. At 250 megahertz, which is our workhorse frequency for utility locating, the antennas are actually 0.3 meters long, about 1 foot. So if I'm working in metric, I'm going to round that down to make the math easier. I'm going to do a line every 25 centimeters. If I'm working in feet, I'm going to do a line every foot. And that way, I'm covering the whole area. And you can see the different, as the antennas get higher in frequency, the physical size of the antenna gets shorter. And so you have to do finer and finer lines. When we do concrete scanning, those lines are much closer together. Because this is what we're trying to avoid. We're trying to avoid a gap in the data. Now, collecting this grid is half the work of collecting this grid. You're going to be out of there a lot faster. But there are gaps. If you're collecting a line, if your antenna is 30 centimeters long and you're collecting a line every 50 centimeters, well, there's a 20 centimeter gap between your lines. And GPR works best when you cross over the target. So yes, you can graze a target and possibly see it, but your best data is when you've gone completely over top of it and you can bounce energy off of it. And Murphy's Law says that if I collect my grid like this and I'm looking for a small object, that object is going to go right in between all those lines and you're going to miss it. If I collect more lines, then I've got a better chance of seeing it. So if I'm looking for a small object, I have to do a grid with tighter line spacing. Now let's look at when we can cut corners. Okay, if I did a grid that was just all the lines in one direction and I didn't collect the lines in the other direction, that would save me half the work. I'd be out of there in half the time. Well, in what situation can I do that? Well, I can do that when I have some clue of the orientation of the objects I'm looking for. A lot of time utility locators they're going to know the general direction that utilities are running. And therefore, if they set up a grid that's perpendicular to that direction, then they're going to cross the utility. Even if it's at a 45-degree angle, they're going to cross it. Or if you're looking for elongated objects, run the lines perpendicular to it and you're good to go. The problem is that if you collect data like this and the object ends up being like this, narrow and parallel to all your lines, and in between two of your lines, you're going to miss that object. So, you know, the best thing to do if you want to cover an area completely is both directions. But there are times when you can reduce the number of lines with a little bit of inside knowledge. Okay, and just a quick thing. When you're collecting data, collect in the first quadrant, please. You learn this in grade 8 math, I think, is that the first quadrant is up here, X to the right, increasing X to the right, increasing Y ahead of you. Your 0, 0 corner, you know, in the southwest corner of the grid. If you do that, then everything comes out and your data goes straight into our software and makes pretty pictures. If you do it in different quadrants, yes, we can fix it in software, but just easier not to have to do that. And why do we do this? Why do we collect a grid? After all this, we collect a grid so that we can get the detail we need. And I'm going to skip over this one. This is just a quick video on how to collect data or how to set up a grid. But I'll point out, as you're collecting the data in a grid, one of the features our systems have is the ability to set it up so that when you reach the far end of the grid, the line automatically stops. So you don't have to stop precisely at the end of the grid. You just shoot off the end and the system will automatically stop the line when the odometer has gone the distance that you said the grid size was. So that's a nice little feature. It is something you can turn off if you don't want the system automatically stopping for whatever reason. Okay, so you work your way through the grid collection, gradually filling in all the lines, and in the end, the goal is to create depth slices of the data or a three-dimensional image of the data. And so if we look at taking the data, the system will process the grid on the spot and give you a depth slice right on board, and then you can start slicing down. And to show you what depth slices look like, here's an example of utilities slicing down deeper and deeper. You can see this arrow moving. And so you're slicing down a few centimeters or a couple inches at a time. And in this particular case, you can see how complex this site is with a lot of utilities at different depths. And so this would have been a nightmare to try to locate all these just by locating and marking on the surface, because there's so many of them at different depths. And so this is the power of grids, and it's worth the time. It is worth the time. I've had many people call up and they've collected a very coarse grid and they can't make sense of it. And so do a finer grid. Spend the time out in the field collecting more data than the same time in the office scratching your head of how to make sense of the data. The other thing is, when you've collected a grid, you have a three-dimensional view of the data. So now you can do things like this. You can look at it in 3 dimensions, spin it around, and melt out the strong reflections from the weak reflections. And in this case, we can melt it out so that we're only seeing the utilities. And I want to talk about the ability of doing a pseudo grid scan. And so I've talked to people about collecting grids for 2 decades now. And while I hope that I've convinced lots of people, I know that I've not convinced everyone. So there is another way of collecting data over an area, and that is a pseudo grid. And in the pseudo grid, you do this. You walk back and forth with the data, again, like you're mowing your lawn. But in this case, we are using the GPS to position the data. So you have to do this with a good GPS on the system. You have to do this with open skies. You can't be under trees. You can't do things that are going to block the GPS signal. and make it less accurate. But when you use the GPS positioning for this, we can cover an area just like this. And then you can take the data and you can look at it in map view, and you can say, yeah, okay, I did a pretty good job covering that area. And then you can now we can't do this on board. We can't process this data into depth slices on the data logger at this point. You've got to take this, what we call the pseudo grid data, onto a PC. And when you do that, you can produce these depth slices. And so here's one where, we can see some high amplitude, some strong reflectors coming through at this level. And then if I cut down to another level, so you can see these two utilities that we've identified pretty quickly by doing a pseudo grid over top of them. Some tips and tricks to help with your GPR data. So remember, crossing utilities at an angle distorts the utility hyperbola. Be aware of that. Always mark the utility at the center of the GPR system, not on the side of the GPR system. Be aware of confusing Ringy responses from metal and puddles and that sort of thing. Be careful that airwaves look like targets in the subsurface, and they've tripped up a lot of people over the years. So do your due diligence, figure out the velocity, figure out if it's actually an object in the ground. Grid scans with a tight line spacing give a more complete picture of the subsurface. Hopefully I've shown you that. And even pseudo grid scans are better than nothing, and they're an easy way to cover a large area. Okay, so those were all the topics I got. I had a few more, but I'm not gonna go over time here. So at this point, I want to turn over to Ron and see if there's any questions that have come in that I can answer.
I'm going to start with a comment that I want you to expand on slightly, if you don't mind. So one of the comments was, so water is good and water is bad. Just give a little bit on that one to start us off.
Salt water is always bad, right? Water itself, like one of the things that drives me crazy is when people say, you know what, I'm not going to do the GPR survey because it rained yesterday. And okay, I never agree with that. The only water itself is fine. And what proves that is people actually use GPR to do bathymetry. You can take a GPR system, put it in a non-metallic boat, float it out into fresh water, and you can see the bottom of the pond or the river or the lake. And so that means that water doesn't absorb GPR signal. Chemicals, the objects in the water, which drive up the conductivity of the water, which makes it saltier, is what absorbs GPR signal. So I've seen a lot of cases where water has actually improved the image of the data. And people probably won't believe that, but it's true. I've seen cases where that occurs. Where it's a problem is where you already have salts in the subsurface. Once the water gets down there and now you have salt water, there's your problem. And that absorbs GPR signal very, very quickly. So that's a little bit about water.
Next question. Can airwaves be interpreted and ignored easily when using GPR inside a building?
Buildings are really tricky because you've got energy bouncing all over the place from every direction. You can get energy bouncing from walls. The most common one you're going to see is off the ceiling. And the ceiling reflection should be dead easy because you should be able to estimate that and say, okay, I've got a metal ceiling that's 30 feet above my head. So if I see a flat reflector that's 60 nanoseconds in the data. The other way, if you don't have a time scale, it's usually about 3 times the depth. So if it looks like it's at about 10 feet, I guess it would be 1/3 the depth. If it looks like it's about 10 feet in the GPR section, triple that, and that would be how far away it is in air. And so buildings are tricky, but especially when you're trying to look deep. The shallow, when you're looking in the concrete or just under the concrete in the building, we can usually see objects like that pretty easily. But then what happens is at that point, you start to see more reflections from walls and ceilings and things like that, just to make it more difficult to interpret.
Very good. And with the use of the radar outside, I am a firm believer in calibrating that velocity. I have had numerous employees over the years spend a lot of time looking for that beautiful hyperbola that if they would have done that, would have known that they were getting the, I think as your example said, the street light in one case or the building. So I thought that was great. Next question. What do you recommend for line spacing when looking for unknown utilities at unknown orientation and unknown depths? And the examples were 200, 250, and 500 megahertz. Is there a recommended line spacing?
Line spacing should be equal to the length of the antenna. So 250 megahertz should be about 30 centimeters or less, 25 centimeters, or 1 foot. If you're working in imperial, that's when I like, 1 foot, one line, 1 foot apart. Now, sometimes people look at that. I have people call up and go, yeah, we're scanning an area that's 4 acres. And you do the math on that and you go, oh man, that's a lot of data collection. But, technically speaking, that's going to give you the best possible data. You can put lines further apart, but then it becomes a connect the dots exercise in saying, okay, the hyperbola I see on line 1, do I think that's the same object on line 2 that's, maybe 5 feet away? Now you've got to have a bit of faith there to say, okay, I think it's the same object. But that is solved by simply having 4 lines in between lines 1 and 2 that fill it in and make it obvious. And I see this time and time again of people just not collecting enough data. I know it takes more time.
Very good. Next question. What is the recommended procedure to make sure you stay online for long lines? And again, not varying from left to right.
It's pretty, I always have orange cones available to me, like those 3 foot tall orange cones. And it's humans are pretty darn good at walking straight at an object if they have it in their vision. So you can put one of those things, 100 feet away and say, walk straight towards that. And most people can do that, certainly with a bit of practice. What normally happens though, people will start looking at the GPR screen because they're interested in seeing stuff. And you have to say, no, don't look at the screen. Look at the screen when you're done the line. And when you're done, walk straight. Your only job is to walk straight. And when you hit the far end, then look back at the data and see, what you've found.
Good. Okay. For next question, for a pseudo grid, is there a plan to have the capability to see the map view while acquiring the pseudo lines?
I want it so badly. One of my jobs is in product development, and I want it. I'm pushing for it. You'll see it eventually.
Awesome. Okay, next question. Would you please explain a little about the effectiveness of the GPR method in inspecting the degradation of the rebar in concrete structures which are in close contact with water, for example, bridges or I think that's dams?
Okay, a little bit out of the scope of what I talked about, but just a general GPR thing. The whole idea on that, GPR does not detect corrosion in rebar directly. It's an indirect thing. And so the best you can do is collect data over a large area and look at all the responses from all the rebar and look for variations in that response. And so, and there's an ASTM standard for this. ASTM 6087, I think, is the standard for this. But the idea is that if you had a perfect bridge deck, let's say it's a bridge deck with rebar in it. If you had a perfect bridge deck, then the response, the signal reflection amplitude of every rebar should be identical. right? If it was perfectly homogeneous and everything was good. So if you start seeing variations in the reflection strength from rebar, now you can start saying, well, why? Why is it weaker over here? Why is there a whole patch of rebar where the responses are not nearly as strong? And one of the reasons for that could be corrosion. Now, we're not saying it is, but we're saying, okay, Mr. Customer, I've scanned your entire bridge, and there's one patch over here that looks different. The responses are weaker or different in some way. And so you say, if you are going to do any destructive testing in order to determine whether there's corrosion in this bridge, this is the spot you should look at. You should punch a core in this area. And if it turns out that the rebar is corroded, okay, this is the worst spot in the whole bridge, according to the GPR. If it turns out that the reason the rebar are weaker over there is because maybe the concrete is degraded, maybe the concrete has been cracked and full of cracks and air or water, that can also change the response in the rebar. And maybe the rebar is absolutely fine, but the material above it isn't. That's about as much as I'm going to say on that topic. There's a lot more to say, though.
Absolutely. Great. We've got, looks like 2 questions left. And then if any questions beyond that, you could just email me. We'll get those taken care of. Next question. What about moisture penetrated into the structures that we are doing the inspection on? Does it reduce the quality of GPR data and or depth of the penetration?
It always, water itself is not going to stop it, but is not going to eliminate GPR signals unless you get in. I mean, technically, when you get up into the very high frequencies, there is more absorption of GPR signal above about 500 megahertz. And that's actually, it's the microwave oven effect. If you think about it, a microwave oven is actually just it's a GPR system with a much higher frequency. It's working in gigahertz. And the reason that a microwave oven works is because the radio waves are exciting the water molecules and making them move. And that's what heats up your food. And so the same sort of effect happens. You start to see it in those sorts of frequencies in GPR. So there is a little bit of absorption of GPR signal from water. But to answer your question, it really depends on what that water, most of the time, what it is dissolving and what's dissolved in it. And if that's a material that gives you high electrical conductivity, then that's going to affect your depth of penetration.
Okay. And last question with a little bit of a qualifier saying that this person is relatively new to GPR. And they want to know if GPR will pick up undocumented short stubs, less than a foot long off of a known pipeline. So So
it's probably tricky. You would probably need to have collected enough data over top of it. As I say, you would likely have to have collected a grid with a fairly tight line spacing to identify that for sure. Because you're trying to see that little stub end. You're trying to see it leave the main pipe and stop in a foot or two. So I think in theory you would see it. In practice, I don't think I could even find a case study example of that.
Yeah, and I think, my comment from going back a long time, just being the field guy using it, was you got to have the tight grid. And my other thought on that is I'm probably not going to know that that's a 13-inch stub, although I may pick a stub coming off, but I'm probably not going to be tight enough that I can get real specific other than knowing something's there.
Yeah, exactly.
Cool. All right. Well, that's all the questions we have for now. Greg, as always, thank you. Thanks to everybody for attending. We will obviously be having Greg back for more discussions to maybe finish out the rest of that presentation. But Greg, great job as always. And thanks to everybody for attending.
All right. Thank you, guys. I appreciate your attendance.